Welcome to this next video in the playlist on ring theory. In this video what we're going to talk about is Euclidean domains. Okay, so we'll start off with the definition of a Euclidean domain, and then what we'll do is have a look at some examples of Euclidean domains. Okay, so the first thing to say is that a Euclidean domain has to be an integral domain. So you have to start off with an integral domain. So we'll start off with an integral domain, which we'll call capital D here. And remember, an integral domain is a non-zero commutative ring, okay, which also obeys the integral domain property, which is that if you take two non-additive identity elements and multiply them together, then you'll end up with an answer that is not the additive identity. So the only way to multiply two elements in an integral domain together and get the additive identity is if either one of them or both of them are equal to the additive identity themselves. Okay, if you take two non-additive identity elements and multiply them together, you will end up with something that is not the additive identity. Okay, so we've got an integral domain, and what we're now going to do is elevate its stature up to a Euclidean domain. Okay, so how do you do this? Now, I'll give you the warning right now, this is a complicated definition, okay, and the way that we're going to get a good understanding of the definition is by doing examples. Okay, so don't worry if you find the definition intimidating initially. Okay, so a Euclidean domain is an integral domain which can have something called a Euclidean size function defined on it. Okay, now what is a Euclidean size function? So a Euclidean size function is a function which we'll call capital F here, which is a map from the Euclidean domain to B, okay, so the integral domain at the moment, without the additive identity in. So you have to take the additive identity out of the integral domain, and that leftover portion of the integral domain, that's going to be the domain of this Euclidean size function, okay, and it's going to map all elements in the integral domain apart from the additive identity onto the non-negative integers, so onto 0, 1, 2, 3, etc. So the natural numbers union 0. So remember, the natural numbers is just the counting numbers 1, 2, 3, 4, 5. But we want 0 to be in there as well. So we'll say the non-negative integers. Okay, so all the integers that are not negative, and of course that includes 0. 0 is not negative. Okay, right. So to draw a little picture of this then, okay, if I draw a little picture of my integral domain here, so let's say this box is representing my integral domain, okay, so this is D, and let's say we've got our additive identity element here. So what we're going to do is we're going to take that element out, okay, so ignore that element, and then all the other elements of our integral domain here, so all of this leftover portion, the integral domain subtract the additive identity, this is then going to be mapped onto the non-negative integers. So to every element of the integral domain outside of this additive identity, so not for the additive identity, but for every other element, you will ascribe to it some non-negative integer, and that's going to be its Euclidean size, if you like. Okay, so this function here is called a Euclidean size function. And I should stress, this Euclidean size function is going to have to obey a really important property. So I haven't finished this definition yet. Okay, so this is a Euclidean size function. Okay, I'll just underline the Euclidean size function in a certain colour. So the function here is the Euclidean size function. So the actual mapping which takes all the elements of the integral domain and associates them with a non-negative integer. And I should stress that in order for an integral domain to be a Euclidean domain, it just has to be the case that it can have a Euclidean size function put onto it. Okay, it doesn't. It's not necessarily the case that there's only one Euclidean size function it can have put onto it. There might be multiple. It's just the case that there has to be one, at least one, that you can do this with it. Okay, right. So this is obviously very easy. You could imagine that you could do this for any integral domain, but the thing is I haven't finished the definition. So let's now see the complicated bit. Okay, so this function, if it is going to be a Euclidean size function, has to obey an incredible property. Okay, and it's this property that really we're going to spend the rest of this video understanding. Okay, so the property then that f must obey is that it must obey what's called a Euclidean division algorithm, or rather it must give rise on this integral domain that we've defined it to what's called a Euclidean division algorithm. Okay, so with this f that you've defined here, if this is going to be a Euclidean size function, it must give rise to something called a Euclidean division algorithm, or you can just call this a division algorithm. Okay, so a Euclidean division algorithm. So what actually is a Euclidean division algorithm? So a Euclidean division algorithm is that if you take two elements, so now I'll state it out. So let's take two elements, two arbitrary elements from our integral domain. So take little a, which is from our integral domain here, capital D, and let's have little b also from the integral domain. However, it cannot be the additive identity. So I want you to pick little b so that it's not equal to the additive identity. A can be the additive identity if you wish, but b can't be. B has to be a non-additive identity element from the domain. Okay, so pick two arbitrary elements, a and b here, and now it must be the case that you can write a is equal to q times b plus r, okay, and r either has to equal 0, okay, so I'll put either r is equal to 0, okay, in which case it has no Euclidean size function value, okay, or f of r, the Euclidean size of r, has to be strictly less than the Euclidean size of b here. Okay, right, and that's for some q is in the integral domain capital D, so q is an element of D. Okay, and don't worry if you haven't understood that, we will talk through this very slowly and we'll have a look at lots of examples. Okay, so either r has to equal 0, or it has to be the case that the Euclidean size function of r is less than, strictly less than, the Euclidean size of b. Okay, so let's say you have picked an arbitrary a from your integral domain, so let's add this onto the picture, so here's a, and let's say you've also picked some arbitrary b from the integral domain, and b cannot equal the additive identity. A could have equaled the additive identity, although I haven't drawn it as the additive identity on this picture. Okay, so you pick two arbitrary elements. I want you to be able to write a is equal to q times b plus r. Okay, now I'll give you a bit more terminology. Q is going to be called the quotient. Okay, so this is the quotient, and r is called the remainder, hence the symbols that I've used for them. Okay, right. So what you need to do then is you need to vary q, so you need to go through the different elements of the integral domain and ask what is q times b. Okay, so you go through all the different elements of the integral domain and you look at what is q times b. Okay, and obviously if you can find a q such that q times b is actually equal to a, then of course a will be a multiple of b, and then you can set the remainder here equal to 0. So that's the first case. Okay, so that's brilliant. You've done it then. Okay, that's absolutely fine. If a is a multiple of b, then this is satisfied instantly, so you don't need to worry about it. If, however, a is not a multiple of b, then for all the elements of the ring that you can put in this position for q here, so you can let the quotient equal whatever you like, go over all the elements of the integral domain, and whatever element you actually pick, it will never be the case that q times b is equal to a. Okay, in this case, if this is a Euclidean size function, and indeed if this integral domain is a Euclidean domain, therefore, you must be able to find some q such that when you use that, so when you times b and q together to get qb here, the r, the remainder that you have to add on to make this truly equal to a, has to have Euclidean size function less than b. Okay, and you must be able to find a remainder always, so whatever q you put here, even if that q times b is not equal to a, you must always be able to find a remainder which corrects this, okay? Simply set r is equal to a minus q times b, okay, and then you've got your remainder, so the remainder will always exist. The question is, can I find a q such that the remainder has size less than the size of b? Okay, and if that is going to be true, so if no matter what a and b that you pick from the ring, you can always do this, you can always find an expression of this form where either r is equal to 0 or at the very least f of r is less than f of b, then this is a Euclidean size function, and then you can elevate the integral domain from just being an integral domain up to being a Euclidean domain. So a Euclidean domain then is an integral domain for which there exists at least one Euclidean size function. Okay, so if you have a Euclidean size function on an integral domain, then that integral domain is now a Euclidean domain. And we are now going to study the incredible properties of integral domains which do indeed have a Euclidean size function on them. Okay, right. So what we're now going to firstly start off with is just having a look at a few examples of this, because that's the best way to get intuition for this. And then what we'll do is go more general and have a look at some of the general results that follow from an integral domain being a Euclidean domain. Okay, so let's start off with some examples, and the major example of a Euclidean domain is the ring of integers. So we'll start off there. Okay, so the ring of integers is where we'll start. Okay, so just to remind you, this is the set of all whole numbers, both positive, negative, and you'll also have 0 in there, with the normal addition and multiplication law that we learnt in school on it. Okay, now, this is indeed an integral domain, since it's a commutative ring that is certainly not equal to the 0 ring, and it does obey that important integral domain property that if you multiply two non-zero integers together, you will end up with a non-zero integer. You can't take one non-zero integer, such as 2 for instance, multiply it by another non-zero integer, such as 3 for instance, and expect to get 0 back again. You'll always get another non-zero integer, in this case 6. Okay, so it is an integral domain. Now let's ask, is it a Euclidean domain? Well, to prove that it's a Euclidean domain, we have to find a Euclidean size function. Okay, so let me give you a Euclidean size function. So remember, this is a function from the integral domain here, which is the integers, without the additive identity in, so all the integers except 0. Okay, so all the negative integers and all the positive integers, but not 0. Okay, and it's going to map us onto the non-negative integers, so it's going to go on to 0, 1, 2, 3, etc., the non-negative integers. And I don't know if there's a good symbol for non-negative integers. If there is, I don't know it. Okay, you can of course write this as the natural numbers union 0, but that seems a bit cumbersome, and this seems always more obvious to write. But anyway, I will just write it out explicitly in this way, the non-negative integers. Okay, and how am I actually going to do this then? So what is my Euclidean size function? That's what it has to do, but how am I actually going to define this? So I'm just going to give you a Euclidean size function and then show you that it is indeed a Euclidean size function, and hence I've put a Euclidean size function on the integers, and therefore it is a Euclidean domain. Okay, so which Euclidean size function am I going to go for? Okay, well, it's now going to take any integer bar 0. Okay, so this doesn't apply for 0, and it's just going to map it onto the modulus of that integer. Okay, so for the positive integers, it's just going to map it onto itself. For the negative integers, it's just going to take the positive value, so negative 2 will go onto 2, negative 10 will go onto 10, etc. Okay, so very, very simple map. So just to make this absolutely crystal clear, let's actually draw a picture for this. So if we have our normal number line picture of the integers here, so here's 0, here's 1, here's negative 1, here's 2, here's negative 2, and I'll just go up to 3 and negative 3. So there we have 3 and negative 3, and of course it will go on and on and on in either direction further. Okay, so how is this function going to work then? Well, the first thing to say is that it does not apply to 0, so get rid of that. Okay, so the domain of this function is not 0, so we get rid of 0, but everything else is going to be in the domain and is now going to have a non-negative integer associated to it. Okay, so let's do this. Well, 1 will have the non-negative integer 1 associated with it. 2 will have the non-negative integer 2 associated with it, 3 will have the non-negative integer 3 associated with it, and so on, for the positive integers, so they all just go onto themselves. So this is the function f here. And now let's do the negative ones. Well, they just go onto the positive equivalent, their additive inverse, if you like. Okay, so negative 1 will go into 1, negative 2 will go into 2, negative 3 will go into 3, etc. Okay, so a very, very simple function. So that's my Euclidean size function to be, but I now need to prove that it's a Euclidean size function. So it certainly does indeed give to all of the elements of the integral domain except the additive identity and non-negative integers. So it satisfies that, excellent. What we now need to make sure is that it satisfies the more complicated property, okay, the division algorithm, the Euclidean division algorithm. Okay, and we've seen this, we've used the Euclidean division algorithm on the integers to prove things about the integers before now. Okay, I mean, we've used it in group theory unknowingly, but now we're really going to look at it rigorously. Okay, so what we want to do then is we want to take an arbitrary a from the integers. Okay, so a is an arbitrary element from the integers, and b is an arbitrary element of the integers except that it can't be equal to the additive identity. Oh, and I should actually stress why we don't want b to equal the additive identity. Okay, so let's go back to our abstract definition here and explain why b can't equal the additive identity, why we have made this condition. Well, if b equals the additive identity, then no matter what you make q, q times b will always equal 0 in any ring. Okay, as soon as you insist on distributivity, that's true. So we'd have 0 here, and therefore r would have to equal a, and of course that would break this. Okay, so if b was allowed to equal 0, then this statement wouldn't be true, so that's why it couldn't possibly be true. Okay, so that's why we don't want b to equal 0, because of course the definition couldn't possibly ever be true if b was equal to 0 here. Okay, but it can happen, it can work if b is anything apart from 0. Okay, if you're working in a special ring, a Euclidean domain, and you've picked this size function sensibly. Okay, and we're going to indeed show that it works here. Okay, so that's why you can't let b equal 0. If you let b equal 0, this definition would never hold ever. Okay, so you'd have a pointless definition there. Okay, so a is some arbitrary element of the integers, and b is an arbitrary element of the integers, except it can't be equal to 0. And what I now want to show is that there always is a q. Okay, so there always exists a q, which is an element of the integers, such that a can be written as q times b plus r, and either r is equal to 0. And I've written this condition out nicer than I did it originally. Either r is equal to 0, or at the very least the Euclidean size of r is less than the Euclidean size of b. Okay, so really this is saying that the remainder has to be smaller than the thing that you've divided out, in a sense. Okay, so I'm using those terms loosely, relying on your intuition from classical algebra. In a sense, what we're doing is trying to divide a by b, failing to do so in some cases. Of course, in some cases a will be a multiple of b, but in some cases it won't. Okay, and then we're putting a remainder on here, and we're saying the remainder has to have size less than b. Okay, what we were, in a sense, dividing out by. Okay, but of course we can't, that's all just using your unrigorous intuition from classical arithmetic rather than rigorous definition. Okay, this is the rigorous definition. Okay, right, so let's show that this is the case then. Okay, so let's start off by drawing a picture of what all multiples of b are going to look like. So remember, we are allowed in our search for an expression here, so start again actually. We've got this a and this b, okay, and you've picked an a and a b, and you have now given me the challenge of finding a q and an r such that this is true. Okay, so I begin my search, basically. I have to search over all q is in the integers to try and find one so that q times b plus a certain remainder will equal a, and this remainder is either equal to 0 or at the very least its size is less than b. Okay, so a natural thing to look at is what are all the multiples of b? What is this q times b? What values can this q times b take on? Okay, that's a natural thing to look at because we are allowed to vary q over any element of the integers. Okay, so let me draw a picture of this then. So here's our number line, and let's now draw on all the multiples of b. Okay, so one of the multiples of b will equal 0. That's when q is equal to 0. Okay, because remember b doesn't equal to 0, but q can equal 0. Okay, then we'll have, of course, b, that's when q is equal to 1. Then we'll have negative b, which is when q is equal to negative 1. Then we'll have 2b, which is when q is equal to 2. Negative 2b, 3b, negative 3b. Okay, so let me just colour code this in. So this is effectively a picture of q times b, all of the different things that I can get as my answer for what q times b is by setting q equal to arbitrary elements of the integers here. Okay, now, a. My element A, either it will be a multiple of B, and therefore it will actually be one of these purple dots. And I should stress, this goes on and on and on. This doesn't end. I hope that was implicitly obvious that it would go on and on and on. I just couldn't be bothered to draw it all. Okay, so either A is one of these purple dots in this beautiful lattice, this beautiful one-dimensional lattice of points evenly distributed. Okay, either A is actually equal to one of those, in which case, of course, A is equal to a multiple of B, and therefore the remainder would equal 0, which does satisfy this condition because r is equal to 0 is one of the options. Or A is not one of these purple dots, but then it must be between two purple dots. Okay, so just putting it arbitrarily on this picture, let's put it there. Okay, so if A isn't one of the purple dots, then it's in between two purple dots. And now here comes the big thing. What I can then do is say, okay, let's pick the purple dot that is just, let's say, I'll go arbitrarily to the left of A. So this is A here. So I can always find the purple dot that is to the left of A. In this case, it will be negative 2b. Okay, I can set q to the appropriate thing to take me to that purple dot that is just to the left of A, and then my remainder is just going to be the bit that I have to add on to take me from the purple dot up to A here. And what can I always say about that remainder? Well, the first thing I can always say is that it will be an integer, okay, because the difference between these two will be an integer step, okay, and the other thing that I can say is that it is going to be strictly greater than 0, because if it was equal to 0 it would actually be the purple dot, and therefore it would have been addressed in case 1, and also that it's strictly less than b, because if it was equal to b you'd get all the way up to this next purple dot. Again, we don't want it to equal there, we want it to be strictly in between these two, and therefore r has to be strictly in between those two. Okay, but what does that now tell us? Okay, if r is in between these two, then what I know is that f of r, the Euclidean size of r, is going to be less than the Euclidean size of b. Okay, I hope that's obvious. If r is smaller than b, they're both positive integers, so the Euclidean size of r is going to just be r, and the Euclidean size of b is just going to be b, so f of r is going to be less than f of b. Okay, so there, indeed now, I have shown you that you can always do this. You can always write a is equal to qb, where you'll set q equal to the appropriate integer to take you to the purple dot to the left of a, and then you can add on r, where r will have size function less than the size of b. Okay, you can absolutely always do that, provided that b is not equal to 0, of course, and we've set that that is the case. Okay, so that's always absolutely fine. So indeed this is a Euclidean size function on the integral domain, which is the ring of integers. Okay, so the ring of integers, we've now got a Euclidean size function on it, so it is a Euclidean domain. So that's our first example of a Euclidean domain. Let's now have a look at some more examples. So my next example is all fields are Euclidean domains. Okay, so I want to show you that all fields are Euclidean domains. Now the first thing I need to show you is that actually all fields are integral domains, because I don't think we've actually ever proven that in the playlist on ring theory. And of course all Euclidean domains are integral domains, so we better first check that, and then what I'll show you is that we can always put a Euclidean size function on a field. Okay, so let's say we have some field, capital F here. Okay, of course a field is a non-zero commutative ring. Okay, but now let's show that it obeys the integral domain property. Okay, so how can we show that it obeys the integral domain property? So we need to show that if you take two non-zero elements, I'll just put this, so let's say we've got A and B from our field, and they are not equal to the 0 element, so they're from the field without the 0 element here. So we've got A and B from our field without the 0 element. Okay, and what I now want to show is that if you multiply these two together, you'll also get something that is not the 0 element. Okay, so I want to show that A times B is not equal to the 0 element. Okay, so how can I show that? Well, the fact that both of these are in the field and they are not equal to the additive identity means that both of them are going to have multiplicative inverses. Okay, I actually only need it to be the case that A has a multiplicative inverse, but you could also do this with B's multiplicative inverse. Okay, so because A is not the additive identity, A will have a multiplicative inverse, 1 over A. Okay, now I'm going to prove this by proof by contradiction. So what I'm going to suppose is that I've got A and B, which are non-zero elements of the field, and let's suppose that they do multiply to give 0, and now I want to arrive at a contradiction. I'm going to use the fact that if A is not equal to 0, its multiplicative inverse exists. Okay, so what I can now do is multiply both sides of this equation by 1 over A, and this is really simple. Okay, so I just multiply both sides by 1 over A, and of course on this side, when I multiply 0 by 1 over A, I just get 0 back again, because anything multiplied by 0 gives me 0. Okay, now I can apply associativity of multiplication in a field, okay, to rearrange the brackets and get the brackets around 1 over A times A here, and of course those will multiply together to give 1, the multiplicative identity by definition. 1 times B will equal B, so now you have concluded that B is equal to 0. Not good at all, because we assumed initially that B wasn't equal to 0. Okay, so there's our contradiction. So if you have two non-zero elements in a field and multiply them together, you will get a non-zero answer. Okay, so a field is an integral domain. Okay, right, so all fields are integral domains. What I now want to show is that there are actually all Euclidean domains. So I need to now find you a Euclidean size function. So let's just do this here. So this is very simple. So we need to find a Euclidean size function which is going to go from our field without the additive identity in it. Okay, so from the field without the additive identity to the non-negative integers, so to 0, 1, 2, 3, etc., that obeys the division algorithm or gives rise to the division algorithm. Okay, so how are we going to do this? Okay, well, it's really, really simple. You just map every element of the field without the additive identity in onto 0. So I'm just going to take an arbitrary element of the field A here, and I'm just going to map it onto 0. Okay, very, very simple. Okay, and remember, it's important to remember here that the additive identity itself doesn't get mapped onto 0. It's all the other elements of the field that are getting mapped onto 0. The additive identity doesn't get mapped onto anything. It's not part of the domain of this function. Okay, so why then does this give rise to a successful division algorithm? Okay, well, let's check the condition. So let's say we've got an arbitrary A, which is an element of our field, and we've got an arbitrary B, which is an element of our field, except it's not the additive identity. Okay, I now want to show that you can find an expression for A, which is of the form Q times B plus R. Well, of course, in a field, you can always find something which will multiply by B if it's not the additive identity to give you A. Okay, so what I claim is that we can set Q equal to A times the multiplicative inverse of B, and this is why it's important that B is not the additive identity, especially in this case. Okay, and if I set Q equal to this, this is perfectly fine to do. The multiplicative inverse of B will exist because we're working in a field, okay, and A of course exists, so I can multiply A and 1 over B together. I will get some element of the field, and I can set that as my Q. Okay, now consider this. A is going to be this Q times B always. Okay, because look, if I multiply this by B, the 1 over B will cancel with this B, and I'll just end up with A here. Okay, so I will indeed get A. So you can see here that any element is a multiple of a non-zero element in a field. Okay, and that means that the condition is always satisfied because R is always going to equal 0. Okay, so you don't even need to consider the Euclidean size function because R is always going to equal 0 in this case. Okay, so it really did not matter what you set A equal to. You could have had everything going to whatever you wanted, basically. Okay, so that's absolutely fine. I'll repeat again, it's because in a field, any element of the field is a multiple of any non-zero element. Okay, you can always find something which will multiply with a non-zero element to give you whatever other element you like in the field. Okay, so the remainder will always equal 0 in this case. Okay, so there's another example, or rather a huge number of examples of Euclidean domains. All fields are Euclidean domains. Now what I want to do is give you one final example, which is going to be a really important example later on. Okay, and this is going to be the ring of polynomials over a field. Okay, so f is going to be a field, and we're now going to generate the ring of polynomials over that field, f adjoin x, if you like. Okay, now I claim that this is going to be a Euclidean domain. Okay, so the first thing to say is that it will be an integral domain because a field is an integral domain, and we know from our study of integral domains that whenever you take the ring of polynomials over an integral domain, you get another integral domain. So the ring of polynomials here is indeed going to be an integral domain. Excellent. Okay, so now what we need to prove is that it's a Euclidean domain. We need to prove that it can have a Euclidean function, a Euclidean size function put onto it, which will then give this ring of polynomials a Euclidean division algorithm. Okay, so how am I going to define my Euclidean size function then? Okay, so this again is very simple. It's going to take any polynomial, of course excepting the zero polynomial, so the zero polynomial won't be mapped onto anything. Okay, it won't be given a Euclidean size, and it's going to just map it onto the degree of the polynomial. And as I say, this is perfectly well defined for all non-zero polynomials. The zero polynomial, of course, doesn't have a defined degree, although some people will tell you that it's negative infinity, but strictly speaking, it doesn't have a degree. We don't bother defining it. Okay, but all other polynomials do have a degree. Constant polynomials are given the degree 0. Degree 1 polynomials are obviously given degree 1, okay, etc. So all polynomials are going to be given a degree, which is going to be a non-negative integer. So this looks perfect. Okay, it is a mapping from all the elements of this polynomial ring except the additive identity, the 0 polynomial, onto a non-negative integer. We now just need to make sure that it obeys the division algorithm, and it's going to obey the division algorithm because of a point that we studied in the video on fields and ideals, okay, which is that we've already seen effectively this Euclidean division algorithm in the context of these polynomial rings over fields. Okay, and we're now just going to use that here to show that it's a Euclidean domain. Okay, so what we need to show then is that you can take an arbitrary polynomial, so let's say a of x here, from the ring of polynomials over the field capital F here, and you can take an arbitrary polynomial, let's say b of x, from the ring of polynomials. However, of course, this one cannot be the 0 polynomial, so I'm going to make the restriction that it's not allowed to be the 0 polynomial. And what I want to show you is that you can find a q of x and an r of x in the ring of polynomials such that you can write a of x, so you can always write a of x as q of x, the quotient polynomial, times b of x, plus a remainder polynomial r of x, and this needs to obey the fact that r of x is either equal to the 0 polynomial or the Euclidean size function, which of course is the degree of r of x, has to be strictly less than the Euclidean size function of b of x here. Okay, so that's what I need to show, that for whatever a and whatever b you can do, you can always find q of x such that the r of x here will obey either this one or this one. Okay, right. Now we've already shown this, as I say, in the video on fields and ideals. What we show is that it's always possible, given a polynomial a of x, which is any polynomial in the ring of polynomials, and b of x, which is any polynomial except the 0 polynomial, it's always possible to find a q of x such that when you multiply q of x with b of x, the remainder that you have to add on is either equal to 0, or what we showed is that the degree of r of x has to be strictly less than the degree of b of x. It's always possible to do that. You can always find a q of x such that this or this is true. Okay, and of course this statement here, which is the way we stated it in the video on fields and ideals, corresponds to this statement here that the Euclidean size function of r of x is strictly less than the Euclidean size function of b of x. Okay, so if you're unfamiliar with this fact that you can divide polynomials in this way, that there is this division algorithm for polynomials, which you will be used to from the context, hopefully, of polynomials with coefficients in the real numbers, if you're unfamiliar with that, do please watch my video on fields and ideals. As I say, we looked at this division algorithm in that video, we just didn't call it the Euclidean division algorithm. Okay, so indeed, this ring of polynomials with coefficients in the field capital F is indeed a Euclidean domain. We have now found a Euclidean size function which we can put onto it, which will give rise to a Euclidean division algorithm and therefore is a Euclidean size function. Hence, this is indeed a Euclidean domain. Okay, so we'll have a break there, and in the next video what we will do is start to study some of the incredible properties that Euclidean domains have. And the first one we will want to look at is the fact that all ideals in a Euclidean domain are principal ideals.